All right, I want to talk through these myAP questions here. So I scanned in my document. I'm going to talk through this because it's a lot quicker of a video when I do it that way. Anyway, we're tossing two die, 1 through 6, 1 through 6. What's the probability that the sum will be 4, given that it's less than or equal to 6? So first of all, we're going to go through and figure out all the ways that the sum could be less than or equal to 6. Less than or equal to 6. So if I roll a 1 on the first die, I can get a 1, 2, 3, 4, or 5 on the second one. If I get a 6, that's too big, so that doesn't count. If I get a 2, I can roll a 1, 2, 3, or 4, and that's good. If I roll a 3, I can roll a 1, 2, or 3, or 4, 1, or 2. So there's 15 ways that the sum can be less than or equal to 6. So within those ways, what's the probability the sum is 4? Well, there's 1, 2, 3 ways that can happen, so it's 3 out of 15. Number 2, so these trees become a pretty helpful tool as you're going through these. So you get this, like, if this happens, then this, but if this happens, then this. So if there's an ice delay, there's a 10% chance of a mechanical issue. If there's no ice delay, there's only a 5% chance of a mechanical issue. So they're not independent events anymore. I can't just multiply them together. I have to make a tree and kind of put things where they go. So there's a 30% of an ice delay, which means there's a 70% chance of no ice delay. If there's an ice delay, there's a 10% mechanical chance of a mechanical. And then what I do is multiply those two together. That means there's a 0.03 probability of an ice delay and a mechanical. So both of those. Same thing down here. So 10% mechanical means 90% no mechanical. So then I multiply here. So 0.3 times 0.9 is a 0.27% chance, or 0.27 probability of ice delay and no mechanical. 70% chance of no ice delay multiplied by 5% chance of mechanical. So we get these. And then in these three, you had a mechanical issue, so I added them up. In this one, it's not a mechanical issue. Some people might have seen this. This would be kind of some next level stuff, but you could have just multiplied right away 0.7 times 0.95. That's the chance there's no issues at all. And then if you subtract that from 1, that would get you ready to go also. Number 3, so this is saying eye color and gender are independent, means it doesn't matter if you're male or female, you're expected to have the same ratio. So there's 120 female students left in this 200 student school. So you would expect 60 out of 80 equal x over 120. You just solve that proportion. Number 4, this is these trees again. So I'm going to play this game twice. I'm going to read what I wrote, but there's a 40% chance the first roll is a 0. There's a 30% chance the first roll is a 1. A 30% chance the first roll is a 2. And then the same thing on the, like I stack that on the end of each of those. And then I add them up because I'm looking for the sum of the scores. So this is a 0 and a 0, 0.4 times 0.4. Sum is 0, 0.16. The sum is 1 here, so I got a 0 and a 1. So 0.4 times 0.3 is 0.12. 0.4 times 0.3 is 0.12. Or 0.3 times 0.4 is 0.12. So hopefully you can see what I'm doing there. And then I'm just going through and figuring out, okay, 0, there's only one way that can happen 16% of the time. 1, well, that could happen here, which is 12%, or here, which is 12%. 2, that could happen here, which is 12%, here, which is 9%, or here, which is 12%. And I'm just going through and figuring out because they want the one that is the most likely. Number 5. So if these two things multiply to give you this third one, so if things are independent, that's what we do, right? If two things are independent, then the probability of them both happening is the probability of A times the probability of B. Well, that's true here. The probability of A times the probability of B gives you this, so they must be independent. They are not mutually exclusive because there is an overlap there. Number 6, another tree is a pretty common one they like to look at. You can think about this with, with a COVID. So let's say 5% of the people have the disease, 95% therefore don't. Well, if you have the disease, you're going to test positive 90% of the time, but there's this 10% false positive, which also pops up. So if you don't have the disease, you're going to test negative 90% of the time. There's a false positive. I can't remember what I said. This is a false negative up here, a false positive. And then again, we multiply across. There's two ways you test positive. You have it and you test positive, or if you don't have it, you test positive. So I'm adding up those two numbers. Number 7, we want to know the probability that at least one motorist is speeding. So there are 5 motorists. I want to find the probability 1 of them, 2 of them, 3 of them, 4 of them, or 5 of them are speeding. Well, that's hard. I do not want to go through and figure out all those. But what I can do is I know that everything in this little bar, all these probabilities have to add up to 1. So if I find the probability of 0, let's say that's like 0.2, well then all the rest of them must be 0.8 because they have to add up to 1. So I'm not going to find the 1, the 2, the 3, the 4, and the 5. I'm going to find the 0 and then do 1 minus that to get to my answer. So the probability that someone is not speeding is 0.6 because 40% of motorists are. But I want none of them to be speeding. So I want 4 motorists in a row, 0.6, 0.6, 0.6, to not speed. That's 0.1296. So that's this number here. And then 1 minus that would give you all the numbers. Number 8 is I'm going to make 2 videos as I'm going through this. It's kind of long, so this will be the last one in this video. Probability of failure for A, B, and C. Well, you want them all to work. What's the probability the device does not fail? They're independent, so you multiply them together. 0.01 of failure means 0.99 of success. So this is 0.97 of success, 0.96. Multiply those together. You'll get that. I'm going to stop, and there'll be another video for the second